All right, so we are going to finish up our building functions from functions lesson. And I just wanted to point out one more time, because I don't remember if I did. When it comes to composing functions, your domain and range, right? So the domain of F needs to intersect the range of G, because what is coming out of G, the range of G, is what's going into F. So as long as there's overlap there, you are going to be able to define it. And what will then the domain of your composition function be will entirely depend on what the two functions are. So it's not necessarily guaranteed that it's going to be the exact same domain as one or other, which we saw when we composed them this way. When we did G composed with F, we ended up with a domain of that composition that was not the domain of F, which was all real numbers, and it wasn't the domain of G, which was from -1 to infinity. So with composition, you just kind of have to see what the function is. Now, when you're doing the algebraic or the arithmetic operations on your functions, adding, subtracting, multiplying, the domain of these first three operations is going to be the smallest domain of your two functions. It's going to be the overlap of your two functions. So in this case, since the domain here was all reals and the domain here was everything greater than -1, greater than or equal to -1, that overlap is just the greater than or equal to 1. And so that was the domain of our addition, sum, and product. With the quotient, you also get introduced a little bit more restriction by requiring that the denominator cannot equal 0. So again, that changed our domain just a little bit. But what I'd like to finish off with now is talking about implicitly defined functions. So, what's the world's most famous relation that's not a function? It's our unit circle, x squared plus y squared equals 1. Its graph is shown below. So this relation is not a function because if you draw a vertical line, it intersects it twice, right? And what is a function, right? A function is a relation with the restriction that any one x value, right, one input has exactly one output. And in this case, there's a positive output and a negative output, right? So this relation, x squared plus y squared equals 1, it's not a function, but it implicitly defines two functions that we can explicitly write. So what does it mean to explicitly define a function? It means you say y equals an expression in terms of x. So how do we start with a relation and find the functions it implicitly defines? You solve for y. So if we solve this for y, right, subtract x squared from both sides, that means y squared is going to equal 1 minus x squared. And then solving this for y, well, if I take the square root of both sides, again, we've got two different parts. We've got the positive square root part and the negative square root part. So we can say that the plus or minus, right, square root of, I'm just going to write it like this, y squared is equal to 1 minus x squared. It gives us that y can equal plus or minus the square root of 1 minus x squared. Now, let's try to color coordinate this. The top half of the circle can be explicitly written as the equation y is equal to the positive square root of 1 minus x squared, right? That's the plus part. And the bottom half of this circle can be explicitly written as y is equal to negative the square root of 1 minus x squared, right? That's the minus part here. So this relation implicitly defines two explicit functions, two functions, right? If I take, and the truth is you can do this for any relation that itself is not a function implicitly defines one or more, and oftentimes well, if it's not a function itself, then it's definitely going to imply at least 2, sometimes 3, or 4, or 5, depending on how crazy your graph is. Implicitly defined functions. So let's look down here. So again, an explicit function is one that can be written in the function notation of y equals some expression only in terms of x. An implicitly defined function is one that satisfies a relation. It's a function that makes the relation equation true. So what I mean by that is this guy right here. Either one of these, if I plug this back in for y, it satisfies my original equation. So let's do that just for kicks and giggles, right? So let's say check, right? X squared plus y squared, which I'm going to write y squared, does that equal 1? If I drop this negative square root of 1 minus x squared, what happens when you square a negative? Well, it becomes positive. What happens when you square the square root of 1 minus x squared? That should give you just 1 minus x squared. So I'm going to end up having here x squared plus 1 minus x squared. And doesn't that indeed equal 1, since my x squared and minus x squared go away and I have 1 equals 1? So yes, this explicitly defined function satisfies the relation x squared plus y squared equals 1. And so too does the positive square root. So they both satisfy this relation. All right, so try on your own right now. Pause this video and please determine the functions implicitly defined by the following relations. Right, so what I mean by that is, again, find the explicit functions, solve for y, right? And then graph the relations, clearly noting which piece corresponds to which explicit function. So go ahead and pause the video and try this on your own right now. All right, so in solving for y, you should have gotten plus the square root of 4x minus 9 and minus the square root of 4x minus 9. And so graphing these right now, if you used your graphing calculator, you could clearly see they make up the top half and the bottom half of a sideways parabola. To figure that out, it's actually easier looking at the implicitly defined relation, the relation, right? If you solve, in this case for x, you've got x is equal to y squared over 4 plus 9 fourths. And again, if the x and the y were switched, would you be able to graph that? Well, yeah, it'd be an opening up parabola with a vertex at 9 fourths, right? 0, 9 fourths. So in this case, with x and y swapped, it's just the opposite. It's x is 9 fourths and y is 0. When y is 0, that's the smallest x value you're going to get, right? So that's where your vertex is. And then, again, I'm all about patterns with parabolas. It's the same thing. My stretch factor is 1/4. So instead of going up 1 whole, I go first up 1/4, and then over 1, and then up. You'll notice I'm saying up, but it's the opposite because x and y are switched. Over 1, the pattern would be 3. So now I'm going to, from here, go over 3/4. 1, 2, 3/4. Then I'm going to go up 1 and then over 5, only in this case 5/4. So it's 1, 2, 3, 4, 5. And then 7/4 and then 9/4 and continuing on. And that's how I drew that sideways parabola fairly accurately. Come see me if what I just said made no sense to you. But let's now see what you can do here. Y squared plus 2y minus 3x equals 5. Well, how do we solve for y? I would highly recommend getting the x on one side. And we want to complete the square. So y squared plus 2y plus what? I'm just going to put this over here for right now. 3x plus 5 plus what you add to one side, you should add to the other. I want all of this to factor into y something squared. So what do I need to do? Take half of b. Half of b would be 1. 1 squared is 1. So I really want this to be y plus 1, because if I have y plus 1, that's going to give me my y squared plus 2y. 1 squared is 1, so be sure you add 1 to both sides. That's going to give you 3x plus 6. So y will equal, I should go slower. Y plus 1 will equal the plus or minus square root of 3x plus 6. So that means y is going to equal -1 plus or minus the square root of 3x plus 6. So my two functions, y equals -1 plus the square root of 3x plus 6, and y equals -1 minus the square root of 3x plus 6. Those are our two functions to then graph, which I'm just going to quickly do. All right, there we have it. Again, graphing this by hand is a whole lot easier once we have talked about section 6 and transformations of graphs. But basically what we can see here, if we look at this, the domain is going to be restricted to x greater than -2. So that's where our vertex of this sideways parabola is going to be. Also, this -1 shifts it down. So from our normal square root function starting at 0, 0, it's being shifted left 2 and down 1. This 3 inside the function has the opposite effect of stretching it. So in this case, over 1 up, not 3, but 1/3. Over 1 up, then 3/3. Over 1 up, 5/3. That finally gets us to a nice, right? So 1, 2, 3, 4, 5/3. That gets us to a nice point. You plug in 1, we're going to get the square root of 9, right? -1 plus the square root of 9, which is 3. -1 plus 3 is 2. And then symmetrically down here, -1 minus 3 is -4. And keep going. So again, I don't expect you to be able to graph these by hand right now, but I do expect you to be able to find the two explicit functions from an implicitly defined, or from a relation that will implicitly define them. All right, let's finish off this section with just a couple application problems. So, example, a fire covers a 200-foot by 500-foot rectangular forest region. Its length is increasing at 4 feet per minute, and its width is increasing at 2 feet per minute. Write the area of the fire as a function of time. When will the fire be 10 times its original size? So let's call this part A first. First, write the area of the fire as a function of time. So here's our initial fire, right? The area of the growing fire with respect to time should look something like this, right? The area is going to be the length times the width, right? So how do we express the length with respect to time? How do we express the width with respect to time? So if we call this my length, initial, and we call this my initial width, what do we see? So its length is increasing at 4 feet per minute. So this side here initially was 500 feet plus an additional 4 feet times t minutes, right? So let's let, with respect to time, t in minutes, right? And so then my width is originally 200 feet plus now an additional 2 feet per minute, so 2t. So what's the area of the growing fire with respect to time? Well, it's just going to be 500 plus 4t times 200 plus 2t. So I'll let you quickly pause the video, multiply that out, tell me what you get. And hopefully you got the area with respect to time. It's 8t squared plus 1,800t plus 100,000 square feet, right? Technically, this is all in feet squared units. So when will the fire be 10 times its original size? Well, its original size was 100,000 square feet. Times 10 is 1,000,000. Subtract 1,000,000, and you end up seeing you get a quadratic that you're going to have to solve. Use a calculator to solve it. It doesn't factor. I tried. And you get about 241 minutes divided by 60 minutes an hour is about 4 hours. So example 5, I will leave for you to read on your own. The solution is provided for you, but it's an example of composition.